In this lecture, we are going to discuss about multiple pulse width modulation. Multiple pulse width modulation technique is used to control the output voltage from a inverter. This is an internal control of inverter circuit. Internal control of inverter circuit. We already discussed about single pulse width modulation technique. In single pulse width modulation technique, a single pulse is produced per half cycle. A single pulse, controlling pulse, a single switching pulse or controlling pulse is produced per half cycle. But in the case of multiple pulse width modulation technique, we are producing several pulses per half cycle. In order, this technique will reduce the harmonic content at the output of the inverter. In single pulse width modulation technique, the third harmonic content is greater. Okay, dominant. Third harmonic component is dominant in single pulse width modulation. In order to reduce the harmonic content, we can go for multiple pulse width modulation technique. Okay, in multiple pulse width modulation technique, there is a reference rectangular signal, and the frequency of the reference signal is determined by the frequency of the output signal. The frequency of the reference signal is same as that of the frequency of the output signal, and the magnitude of the reference signal is AR, and the frequency of the carrier signal is FR. Frequency of the carrier signal is FR. Carrier signal is a triangular signal. We are comparing a rectangular reference signal with the carrier signal, and we are obtaining a output gate signal, and this gate signal is used to gate our switches Q1, Q2 and Q3, Q4. Okay. The frequency of reference signal sets the output frequency F0, and carrier frequency Fc determines the number of pulses per half cycle, small p. Number of pulses per half cycle. This is the number of pulses per half cycle, small p. Okay. Here p is equal to 5. Here there are 5 pulses per half cycle, so small p is equal to 5. The modulation index controls the output voltage. Modulation index controls the output voltage. This type of modulation is known as uniform pulse width modulation. This type of pulse width modulation is also known as uniform pulse width modulation. The number of pulses per half cycle. We can find out the number of pulses per half cycle. P is equal to number of pulses per half cycle. P is equal to Fc divided by 2 F0, where Fc is the carrier frequency and F0 is the output frequency, and which is equal to MF divided by 2, where MF is equal to Fc divided by F0, and it is defined as the frequency modulation ratio. Frequency modulation ratio. If small delta is the width of each pulse, the RMS output voltage can be obtained by the equation V0 is equal to 2p divided by 2 pi into integral pi by p minus delta by 2 to pi by p plus delta by 2 Vs square d omega t the whole raised to half, that is equal to Vs into root 2 p delta divided by p, where p is the number of pulses per half cycle and delta is the pulse width of each pulse. The variation of the modulus index M from 0 to 1 varies the pulse width delta or d from 0 to t by 2p or from 0 to pi by p, and the output RMS voltage from 0 to source voltage Vs. General form of a Fourier series for the instantaneous output voltage is V naught of t is equal to sigma n equal to 135 to infinity Bn into sin n omega t. The coefficient Bn can be determined by considering a pair of pulses such that the positive pulse of duration delta starts at omega t equal to alpha and the negative one of the same width starts at omega t equal to pi plus alpha. Then consider the harmonic profile of the multiple pulse width modulation. This harmonic profile shows the variation of modulation index for 5 pulses per half cycle. The order of harmonics is the same as that of single pulse width modulation. The order of harmonics, that is first order, third order, fifth order and seventh order. The distortion factor is reduced significantly compared with that of single distortion factor. This distortion factor reduced significantly compared with the single pulse modulation. However, due to large number of switching on and off process of switches, the switching losses would increase. With larger value of number of pulses per half cycle, that is P, the amplitude of lower order harmonics would be lowered. The amplitude of the lower order harmonics would be lowered, but the amplitude of some higher order harmonics would increase. However, such higher order harmonics produce negligible ripple, or we can eliminate this higher order harmonics with the help of filters. Due to the symmetry of the output voltage along the x-axis, even harmonics are absent in multiple pulse width modulation. Only odd harmonics are present in multiple pulse width modulation technique output voltage. Okay, compared with the single pulse width modulation, we can reduce the magnitude of the lower order harmonics magnitude in multiple pulse width modulation techniques. That is the comparison of multiple pulse width modulation with a single pulse width modulation. In single pulse width modulation, there is a single pulse per half cycle, but in multiple pulse width modulation, there is several pulses per half cycle. Okay, the number of pulses per half cycle is determined by the frequency of the carrier signal Fc. Frequency of the carrier signal determines the number of pulses per half cycle, small p. Okay, next is the frequency modulation index. Frequency modulation index is the ratio of carrier frequency to reference signal frequency. The reference signal frequency is the frequency of output voltage of a inverter. Okay. Then the frequency modulation index is Fc divided by F0, where Fc is the frequency of the carrier signal and F0 is the output frequency, that is same as that of the frequency of the reference signal. Okay, that is multiple pulse width modulation.